constant here. So under standard conditions, we can relate the delta G to K. And by standard conditions, another thing it means here is, it's like this idea, if you mixed 1 molar of everything, and you put it all together in a beaker, 1 molar of A, 1 molar of B, and 1 molar of C, you put that all in a bucket together, and you just decide, okay, which way is this reaction going to go now? That's what we're talking about when we talk about standard conditions as we're solving for delta G. I've put one version of this in the box, and that's the version we're going to use. If you ever had a really tough question and they wanted you to solve it for K, the second version of this equation shown there, K equals little e to the delta G over RT, that's just the same equation rearranged. This is the one we're going to use. And when we use this, our delta G, that's just our Gibbs free energy. It's going to be in kilojoules. R is the ideal gas constant. But if you remember, there were like 3 or 4 different ideal gas constants you could possibly use, and we always used just a couple of them. The one we use for this, I'm going to check it. I think it's 8.13. Let me check that though. Joules per mole Kelvin. So this is not 0.0821, not 62.4, the one we used a lot before. These are all those ideal gas constants that are on the back of your periodic table. Oh, I got it. So it's 8.31, not 8.13. 8.31. That's what you'll use for R. All right, T is your Kelvin temperature. Most of the time you'll use 298 because that's standard condition, standard temperature. Ln, that means natural log, so you have to use the natural log button on your calculator again. And then finally K, that's your equilibrium constant. So it seems kind of intimidating and stuff at first, but actually you'll be given an equilibrium constant. So if you have the calculator, you'll be able just to put in negative 8.31 times the Kelvin temperature, which is probably going to be 298 Kelvin. And then you just hit that natural log button on the calculator and put your K value in there for that. And the calculator will take care of all the calculations. What we're interested in is getting an answer and finding out if it's positive or negative, and then maybe comparing the different values of one reaction to that of another. On most of the problems, you just have to tell me if it's positive or negative. There's just a few where you might actually solve for it. So this was the problem on the handout that we got at the very beginning of class. I don't know why I put that one out at the very front when we did the other part first, but that's how I left it on Friday afternoon. So this is the kind of question where we can go through all the different relationships between equilibrium constants and delta G values. Hey, still here. I gave out intros while you were out too. All right, so for a certain reaction, K equals 2.53 times 10 to the 8th. Is K bigger than 1 or less than 1? It's a big number, huh? So at equilibrium, do reactants or products predominate? Very good. Products predominate because K is greater than 1. right, now let's take it into a delta G discussion. If K is greater than 1, then when that reaction hits equilibrium, actually on its way to equilibrium, so the whole idea is, again, you're mixing 1 molar of everything in a bucket, you find out which way does the reaction go on its way to equilibrium. So would it have a positive or a negative delta G? Negative. If K is greater than 1, product predominates, so that reaction tends to go forward. It's favored in the forward direction, so it has a negative delta G if K is greater than 1. Again, because K is greater than 1. Is the reaction expected to be thermodynamically favored under standard conditions? Yes, because delta G is negative. So far this stuff is pretty straightforward as long as you know those relationships on the board over there. But then the last little part is using that equation. It's also pretty easy, but it's an intimidating equation because it's got negatives and that R value and natural log and everything. But it's not that bad. Calculate the specific value of the change in Gibbs free energy, the delta G, under standard conditions. So if you mix up 1 molar of everything and put it in a bucket, what would the delta G be as it's going toward equilibrium? Well, here we go. Delta G equals negative RT times, I'll use parentheses here just so we can see what we're doing, times the natural log of the equilibrium constant. So in this case, delta G equals negative 8.131, I keep saying it wrong, 31. That's joules per mole Kelvin, so this is going to give us an answer in joules. Times the temperature. Standard conditions, we'll use 298. That's room temperature there. It's 298 Kelvin. I think that's what we're using on most of these. Yeah. Times the natural log of 2.53 times 10 to the 8th. I'll do that natural log part first as far as my order of operations go, and then I'll just multiply it times those other two numbers. The natural log button, it already puts it in parentheses for me. 2.53 times 10 to the 8th times 298 times negative 8.31. And I'm getting about negative 48,000. At this point, this is still joules because that 8.31 number gives me answers in joules. So right now, I'll just put it in joules, negative 47,900 joules. If they wanted me to put it in kilojoules, I would call that negative 48.9 kilojoules. Sometimes we'll see that as kilojoules per mole. And again, it's just a negative delta G. Negative delta G's mean the reaction is favored to go in a forward direction, which is why you end up with more product to the reactants and you have that K value greater than 1. Yeah. Yeah, thank you. I started rounding it and then I decided to go with 3 sig figs. Thank you very much for paying attention and showing me that. So that's what you'll start class with tomorrow, but again, I'll give you like 20 minutes at the beginning of class tomorrow to do the first page of the homework, but that's what it's all about. So that's the easy part of of today's lesson. If you want to start working on it now, get a head start while we're in here, or you've had a lot to do today. So make sure more than anything that you try to finish up those KSP practice problems if you haven't already done so.